Hey everyone, welcome back to another episode of Neural Networking with Konverge. I am your host Ketan co-founder and CTO here at Konverge. Today we are absolutely thrilled to have a true innovation leader with us on the show. Joining us is Dr. Prith Banerjee, the Chief Technology Officer at ANSYS, a world-renowned leader in engineering simulation software. From holding leadership positions at some of the most prestigious organizations across academia and industry to authoring over 350 research papers, you heard it right, and 2 books, Dr. Banerjee's career trajectory is nothing short of phenomenal. His passion for innovation extends beyond the walls of ANSYS. Dr. Banerjee authored a book by the same title which explores how large companies can collaborate with academia and startups to drive disruptive innovation. We are incredibly fortunate to have Dr. Prith Banerjee with us today. Welcome to the show. So let's now begin with the set of questions for which I'm sure that our audience are eager to get answers from you. So here's the first one. So how can generative AI be leveraged to enhance the accuracy and efficiency of engineering simulations, as you come from that background of engineering simulations?
Absolutely. So let me for your audience, explain the role of engineering simulation and the challenges we face, right? So engineering simulation is used to do product design and innovation. So, and we serve customers in different verticals like automotive and aerospace and energy and high tech and healthcare. So let's take a automotive, designing a car. So when you're designing a car, you come up with a conceptual design, a requirement of a car that the car has to, it's an electric vehicle. I want to design an electric vehicle that will go from 0 to 60 in 1 second in a range of 1,000 miles. So you start with a requirement and then you essentially start designing the car. The car will look like this. You enter those designs in a CAD, electrical CAD or mechanical CAD model. And then you do simulation to simulate the car, right? So you have to simulate the motor in the car, the battery system in the car, the electric powertrain, and you say, hey, is it actually going at 0 to 60 in 1 second or not, right? So the way engineering simulation works is we rely on physics. So there is structural physics, which is governed by partial differential equations called Euler equations, or fluids physics for external fluid flow, which is Navier-Stokes equations, or electromagnetics physics, which is Maxwell's equations. So basically the world around us is governed by physics. Physics doesn't lie. And we take those partial differential equations and we solve them numerically using methods like finite element method, finite volume method, finite differential time domain method to solve the problem, right? Now, the challenge in this world is you can take a particular, what is a finite element method? It's taking a problem which is in 3 dimensions and in time, and you're discretizing the space dimensions. So you're taking a finite element, a small little chunk in XYZ dimension. And for that finite element, you're saying, how will it evolve in time, right? So based on the equations like Euler equations or Navier-Stokes equations. So you have a car and you break it up into 1,000 elements, 1,000 small elements, and based on the 1,000 elements, you can come up with an accuracy of simulation. Okay, and it will maybe 10% is accurate. So it's not accurate enough. So then one way is to say I'll increase the number of finite elements from 1,000 elements to 10,000 elements or 100,000 elements. If I do 100,000. Yes, it is finer and therefore it is more accurate. So the accuracy goes to maybe, the error goes to instead of 10% to say 1%. But in the process, my runtime goes up from, instead of running in 10 hours, it runs 10,000 hours. Oh my God, that's too much. Oh, I've made it too accurate, too long. Let me adjust. So instead of 100,000 elements, let me give 50,000 elements. So in our world of engineering simulation, right? The trade-offs that we have are I can do different meshing, I can adjust the speed and accuracy, right? So trade-off is between speed and accuracy. And also there are things called robustness and ease of use. So if everything has to be done by the human, That's really tedious and it's not as easy to use. You can get something very accurately, but it took like 1,000 hours of time for a smart a PhD from MIT to solve the problem, which is clearly not a problem. So can I make it easy to use? So it just looks at the specification and just sets the right meshing. Oh, you should use mosaic meshing, or you should use tau meshing or pi meshing, and with this grid size, and it just does the thing for you. That's the holy grail. So today, when engineering simulation is used by an analyst, there's a human designer that goes and says, I will use pi meshing. I will use, instead of 10,000 elements, I use 100,000 elements. So the designer does all those choices and then runs the simulation. AI has a role to play in many areas. First is you can actually use AI to speed up the simulation itself. You can run a ANSYS mechanical, right, a mechanical solver, and you take an input condition, a boundary condition, run the solver, look at the output, and say, here's the input, here's the output. And you train an AI model. You know your readers, listeners know about convolutional neural networks. You have a 6-stage neural network, and there are weights on the neural networks, right? So you start with some random weights,
Yes.
and you say, here is the input with some random weights, here is the prediction on the neural network, and my output is not correct, so there's an error. So you do back propagation, you try to adjust the weights so that the error becomes zero for that input output condition. Once you do this, you have a set of weights, you take a second input, run the solver again with the prior weights, and you say, yep, well, again, there's an error. Oh, I need to fix the error. So I do backward propagation again. I do this 1,000 times. The AI model learns what it is that he is trying to solve. And next time, when you have a different CAD model, I give the input condition, the CAD model, and out, instead of doing a PD solver, I use AI trained model to replace the PD solver, the numerical methods, with AI. This is what we have been doing with a tool called Sim AI that ANSYS just launched this year, and it just runs 100 times faster, right? So it's very, very beautiful. The other thing that Gen AI does is use Gen AI to make the setting of the parameters easier, right? So, you should use, so it's not using AI to generate the model, but it's using AI to do the settings of the solvers. And we have actually done both for the ease of use and to speed things up.
Wow, I mean this is an amazing example you gave, and in that you talked about that automobile example at the beginning. So we could get that in that from that automobile example and the mechanical solver that you talked about. That there is a simulation tool and there is a design process. So these two they go hand in hand. So my next question is about that only, that how can generative AI or AI be integrated with simulation tools to accelerate the design process and explore a wider design space, leading to more maybe innovative or optimized products.
Absolutely. And so now let me go back to the same thing that the human designer does. The human designer says, I have to design that automobile, that car, right? It starts with the system level specification of the car and says, for this, I need to have a battery, I need to have a motor, I need to have electric powertrain, wheels, and so on, right? So you start with the system level description, do the subsystem design, the component design, and then you start doing the design of the motor. Separately, you do the design of the motor, then you do the design of the battery system, then design of electric powertrain, and then you integrate the whole thing together, and that's your car. Now, in the process, engineering is all about trade-offs, right? So you can say, I'm going to start with an electric motor, with a 1 horsepower electric motor, right? The 1 horsepower electric motor has 52 rotors and 22 stators and so on. So with 200 coils, and it gives this much kind of power, right? Boost and so on. I do it, but the size of the motor is a little too bulky and it doesn't fit inside the engine hood. So in the world of engineering, it is all about trade-offs. So you can imagine a part like this phone that I have in hand. I can do the phone with a length of 6 inches and a height of 2 inches. And I do a simulation to see, is it Does it have the right electromagnetic property or not? Or I can say, instead of this, I can have this other shape, which is maybe instead of 6 inches, it's only 4 inches long and 5 inches wide. Or maybe 9 inches long and 15 inches wide. Right? So essentially, you have 1,000 different possibilities. The human designer would say, let's try this, takes 2 hours. Let's try this, takes 2 hours. Oh, and now I have to actually connect up the mechanical solver with the fluid solver because I'm designing the car and the car has a shape. And when the car goes at 60 miles per hour, there is fluid flow happening over the car and the mirror, right? And so what is the turbulence that is happening? And because of the turbulence, it's creating drag. Right. And so now I have to do a multi-physics simulation, a structural simulation with this thing, and the motor simulation with electromagnetic simulation. So it's a true multi-physics simulation that we have to do for the car. That's the problem. But I have to get an optimized car, not just one car, the car that will go from 0 to 60 in 1 second and with the range, and it is the most beautiful car and is the cheapest car, right? So in engineering, it's all about optimization. And the human designer was today doing each of those 1,000 different designs and giving it to the tool, right? And it just takes, it's very hard to say, hey, have I checked for all these things, right? As you know, in the world of optimization, you can have local minima. Even you are going down, 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 and then, oops, it is a local minima, and they come up. But you say, oh, I've reached the local minima. But if you were to do a slightly different search, you will go to the next local minima, right? So in the world of optimization that I know your readers are aware of, right, it is a really complex thing. So how do you do optimization of this multi-physics, multi-domain, multi-scale area, right? It is very hard for a human to take care of it. That's where Gen AI and other things come in, right? And essentially, can I build a workflow? So we have a tool called OptiStime that takes that workflow and will automatically generate the 1,000 different designs. And then inside the design, it will run our multi-physics solver, Fluent, or whatever, right? So that's like what is called brute force parametric design. We use AI in OptiStime by saying, suppose I'm doing 1,000 different designs, and each of them are taking 100 hours. That's 100,000 hours of runtime. It turns out that among the 1,000 designs, let's take the first 100, say maybe 200 designs, use it to train the AI model. And once that AI model is trained, instead of taking 1,000 hours per run, that will run in a minute. So it speeds up the process. So essentially now if you can do it in a minute, instead of doing only 1,000 different iterations, I can do 100,000 iterations, which allows you to get to that absolute optimal design of the car.
Nice. Got it. So as I could see from the first two discussions that we had, that it is about speed and accuracy and the parameters
and ease of use
and ease of use. Yeah, that was the fourth one which I was going to ease of use.
So now the fourth thing is the real power of generative AI is generative design. Remember, I started with a problem statement saying that I need to design a car which will go from 0 to 60 in 1 second and a range of 1,000 miles. Now, you, Ketan, you are the mechanical engineer, say, oh, for 0 to 60 in 1 second, 60 seconds, I need a motor based on prior knowledge. I say, I think I need a 5 horsepower motor, right? Or you say, I need a 100 horsepower motor. You have that knowledge in your head. The Gen AI can take the statement that you have and say, based on prior designs, what kind of motor should I have? Should I have a 1 horsepower, 2 horsepower, 3 horsepower, etc., right? And you say, I need a range of 1,000 miles. You, in your head, know, therefore, I need a Panasonic battery stack of this many cells, of 1,000 cells, and so on, based on prior designs. Again, with Gen AI, you can look at all those PDF files, and say, hey, for this car, I've used this, etc. So I do this. So from a specification, Gen AI can generate the first design. Not only can it generate the first design, it can generate 100 different design options. So something that I was saying, I need to take this rectangle and say, do it for 6 by 4, 5 by 9, 9 by 12. Instead, the human saying what those 15,000 different designs are, the Gen AI will create those designs automatically based on the specification. and we'll run the simulation to test it and give the designer the top three designs. And then the designer goes in and says, oh, I like this, I don't like it, and so on. So this is the opportunity for Gen AI.
Right, and I can see that there is a direct impact on the productivity as well with the ease of use coming in. So this is a great example that you gave of the automotive sector, but I'm sure that it applies to other sectors as well. So the next question is about that. What are the most promising applications of generative AI/AI in the aerospace and energy sectors? And if you want to add more to the automotive one, then to the automotive one as well, that will drive significant industry transformation.
Absolutely. So in our area at ANSYS, we, as I said, we work with 5 key verticals. We work with automotive companies, and in the automotive, so that you understand, right? There are the OEMs like Tata Motors or Volkswagen or BMW or Mercedes, right? They actually assemble the car. They are the OEM, but they assemble the car based on systems that they acquired from the tier one suppliers like Bosch or Continental or Aptiv. And then the Bosch and Continental, actually, I was meeting with one of the tier one suppliers today morning, right, just before your call. And then they will use this thing. Suppose you're doing a power steering or a power brake, right? That thing has to run on a embedded control unit from Infineon or NXP. So I'm talking with a Bosch, a Volkswagen car using a Bosch tier one supplied power braking system running on an Infineon CPU. We ANSYS provide the simulation solution to the tier one, tier two, and the OEM. In the aerospace area, the result is the similar thing, right? So we work with the OEMs, the Boeing, Airbus, the people who make the airplanes, and the people who make those fighter jets, from the F-22 fighter jet, the Lockheed Martins and the General Dynamics and so on. And then for an airplane, you need engines. So you have engines like GE or Rolls-Royce engines, right? And then to control the engines, you need software from, say, Honeywell or whatever, right? So we work with all the people in the aerospace area, the OEMs, the tier one suppliers like the engine companies, and the tier two suppliers. In a typical airplane from, say, Boeing, you have 30,000 suppliers. For a car company, you have 10,000 suppliers. So when you're talking about that vertical, you're talking not just the end OEM, but the whole slew, right? And so then let's move to the energy vertical. So the energy, we used to work with the typical areas of energy, the fossil fuels, oil and gas, upstream, downstream, right? All the oil wells and how do you do with all the rigs and so on. The new world is renewable. So it is wind farm. So in a wind farm, you have a wind turbine, right? You have seen all those wind turbines that go to place and so on. You have wind coming through and the turbine is turning. So it's a fluid mechanical interaction, and based on it, the motor is going and is generating power. So we can simulate the whole wind turbine. We can simulate a whole wind farm, meaning a set of 100 wind turbines and you have wind going in Nevada desert, right? Mm-hmm. You can say, where should you place those wind turbines to get the maximum output? Or in the area of solar, right? Solar cells. You have solar cells and the sun rays attacking here, and based on it, you have those electric signals coming out. So we have optoelectronic simulation capabilities we can simulate. So we can simulate nuclear power, right? We can simulate small modular reactors. So we have gone into the energy area about oil and gas, wind, electric, battery, solar, etc., etc. Fourth vertical is high tech. So chips, all the chip companies. So Intel or AMD making the CPUs, or NVIDIA and AMD making the GPUs, or Qualcomm or Broadcom making the wireless chips, or the cloud companies, right? The hyperscalers, the AWS or Microsoft or Google or Meta. So all of those use simulation to build a data center, build a chip or whatever. And the final vertical is healthcare. And within healthcare, we have medical device companies like Medtronic or Boston Scientific making pacemakers, and then pharmaceutical companies making drugs to treat, say, COVID, right? And they use simulation also. So across these 5 verticals, all of them use simulation. Simulation is based on physics. Physics is based on is modeled by partial differential equations, solved by finite element methods, etc. But they take a long time to run. So we use AI and high performance computing, HPC, massively parallel machines, GPUs to speed things up, running them on the cloud. So we are using AI, HPC cloud to speed up our simulations and across these different verticals.
Got it. Got it. Now, moving on to some other parts, so we know that you have written a book, The Innovation Factory, and I wanted to highlight a few things from the book with your experiences that you have had, especially with startups. So my question was that given your experience with startups like Cascade, Geminus, and Neural Concept, and as mentioned in your book, The Innovation Factory, how can established companies effectively collaborate with startups to drive AI innovation?
Thank you. So thank you for Ketan for asking. I have the book right in front. So this is the book that Ketan was talking about, Innovation Factory. And so the reason I wrote the book is, Ketan, as you know, I mean, I was fortunate in my career to have experience in academia. I spent 20 years in academia as a professor at University of Illinois Northwestern. I was involved with starting two very small EDA startups, Excel Chip and Banner Chip, which I sold to other companies like Xilinx and Quickster Media. In the last 15 years, I've been working in large companies like heading up HP Labs worldwide, and then being the group CTO of ABB, group CTO of Schneider Electric, and now CTO at ANSYS. So what I've seen innovation in the setting of an academic, like where researchers are doing fundamental research, writing publications and producing graduate students. I saw innovation in a startup setting, right, where there's really interesting startups come up with very niche, disruptive innovations. And then you have large companies like HP and ABB and ANSYS trying to do innovation. So the key thrust of my Innovation Factory book is that large companies like ABB, Schneider, ANSYS, right, they do the Horizon 1 innovation very well, meaning they have a product like HP has the laptop, right? And they will absolutely nail the next version of the laptop, right? Because they say, oh, we should add more clarity to the screen, softer things, faster processors, more GPU, more version. So they have a product in front of customers. They absolutely know how to do Horizon 1 innovation. Horizon 2 innovation is, I am HP, I want to go to the cloud, right? And so that is also possible. But for a hardware company to go into disruptive areas, right, software is actually very hard. And that is where large companies struggle. And what I say in my book is for the large companies to practice sort of to be like Apple, to come up with an iPhone, right? Or to be like AWS and Amazon and come up with a new thing like AWS, it requires you to do for partnerships with academia and with startups. So now to your question, how can large companies do partnerships with startups? They can work with startups like Konverge, right? And say, hey, I am trying to do this piece of work, right? And I can try to invent it. I can try to invent the iPhone by myself, or I can scan the different startups that are in my area and say, hey, what are they trying to do? And once they do the scanning function, they should try to say, hey, if I take this startup and add it to my portfolio, right? As I mentioned in my book, we had this company called Dinardo that has a tool called OptiSlang that I just mentioned. And OptiSlang plus our solvers would provide real large value. And so then we do the partnership, we integrate the things technically, then we take it to customers and say, hey, this joint solution, does it make sense or not? And if it shows success, not for one customer, but for say 5 customers, it's repeatable. Then you do a business partnership, like an OEM partnership. This startup is selling this thing for say $100. You say, hey, I will sell it for you. And every time I sell it, I'll give you maybe 30% royalty or some number, right? Which is part of the OEM agreement. And so then we both win because the startup has a technology, that technology is being integrated with my larger company, and we both make money in the process. And then if it actually works, we go and buy the company. So it's a multi-step engagement. It starts with a scanning function, then the technology integration, then working with customers, then doing a business with an OEM relationship. Somewhere along the way, you may invest in the startup and then buy the startup.
Right.
Acquisition is a very, very important way
Important way.
to bring new innovations to a large company.
That's a great perspective that you are giving about innovation, because it is always that, if we bring some perspective from outside, there is always a freshness to it, and how we kind of incorporate the freshness in our environment as well. Sometimes that also is a key
The
success
important
metric.
part I will tell you is, and people know this story, that Xerox, as a company, they were doing sort of analog printing, right? They were in the analog printing
Right.
area and so on, and they kind of, oh, I'm sorry, not Xerox, Kodak, right? They were making analog printing, and they saw that digital printing is coming, right? They had all the resources. They knew digital printing is coming, but the reason they did not embrace digital printing is because if they start doing digital printers, their cash cow business of analog printing, bringing 90% of the revenue, would get hurt. So large companies, even knowing, they are not stupid, they know that this is coming, right? They oftentimes choose not to do it. Now, a company like Apple, right, when Steve Jobs are top, right, they have this thing called the iPod. I don't know if you remember the
Yes,
iPod,
yes,
the
yes. I
music player.
remember it. Yes.
And they were coming up with the iPhone. And the iPod business unit leader said, hey, this iPhone is going to kill my business. And a normal company would say, oh my God, let me protect iPod, therefore not bring the iPhone to the market. But Apple being Apple, Steve Jobs being Steve Jobs, says, if somebody will disrupt this business, I might as well be me disrupting the iPod business. And that is the right way of doing it. Most large companies go the Kodak route, and they fail to see the things, right? As Motorola failed to see journey going from the analog cell phones to the digital cell phones, and they were hit by competition, right? It's not that the Motorola engineers did not know about digital.
Of
They knew
course.
about it,
Yes.
but they wanted to protect their cash cow, right? Their analog business. And so this is where the partner should be the start. A startup doing a digital printing, they have nothing to lose, right? They have zero revenue. So they can absolutely do investments in that area. And so for the larger companies, it is better off doing a two-pronged strategy. Keep your analog printing business and partner with the digital printing startup and do all the relationship, grow your business. And when this is stronger, kill your digital printing, analog printing, and move in there. For example, Oracle, right? They are an on-prem database, whatever company, right? And they said, oh, this cloud is not there, etc. Oh, Salesforce is in cloud. They invested in Salesforce. I mean, Larry Ellison actually invested. So my point is that for a large company, you have to protect your current business, but the way you do go into new areas is by investing in the startup, doing the partnership, and bringing innovations. Let me give you an example. People talk about Google as a very innovative company, right? The real innovation at Google was the search. I mean, you use Google for search, right? And with the search, they had a way to monetize with ads. But how much time do you go in a day where you are doing search? Maybe 1 minute in it out of 24 hours. So you are not, Google could not give ads to you for the remaining 23 hours and 99 minutes and 10 minutes. Whereas you are watching Facebook for 8 hours. So they said, hey, if I have a product like YouTube, where people are watching cat videos or your videos and so on, right? If I make it part of my thing, I can use the same mechanism to put ads and generate. So they bought YouTube and integrated the same ad sharing mechanism on YouTube, and look at where YouTube is today, right? Look at Android. I mean, Google saw that it is going from doing search on the laptop, on your machine, on Windows, to search on the phone. So what they did is they bought Android, the platform for the mobile devices, made Android open source, pushed it out, right? So all the phones are doing this and having the search on that Android phone. So you may say, oh, Google did not innovate. Absolutely, they innovated. They innovated by identifying YouTube and bringing that part of it, identifying Android and bringing it part of it. This is how large companies innovate. You don't have to organically develop anything. You have to have a strategy, which is what I do in my role as CTO. I'm always looking for opportunities and then either building the technology myself with organic R&D or with partnership with startups or with academia.
These are all great business use cases or examples you gave, and you also touched upon the point of how CTOs of large companies should think. The last perspective or point you brought, organic as well as the inorganic
Yes.
relationships that you try to forge. So now, moving on, there has been lately a lot of talk about how AI is being used, or it is going to be used in future, and how are we going to go about the responsibility of AI, or the how do we bring the trust and the accountability. So my next question is regarding that, that what key ethical considerations must be addressed as AI becomes more prevalent in these industries, and how can we ensure responsible AI development and deployment both?
Absolutely. This is a huge problem. And one of the things that a human intelligence is good at is they can make the right trade offs in life, right? Because we are humans. And an AI, without lacking that sort of ethics, will oftentimes make a wrong example. So I will give you an example that I know the AI people already know, but to make the point, right? Suppose I have an AI driven car, right? An autonomous car, and I am driving, and suppose I am driving a car myself, and I am, say, a 60-year-old old man driving, and I see a school bus with 50 children, all 2-year-olds, right, sitting in the bus, right? And the car is then about to crash. The 60-year-old man ethically can make the choice, you know what, I'm going to sacrifice myself, go off the highway, go down the ravine to save those 50 children, because the 50 children's lives are more important. That's the ethically correct decision. The unethical correct thing would be, I should just save myself. The hell with those kids, right? That is unethical, right?
Right.
An AI system, autonomous system driving the car will protect the human, will not see, may not see the case that you are making a trade-off between saving my own driver and the 50 little children sitting there, right? And that those 50 children's lives are a lot more important because they have like 60 more years ahead. This 60-year-old man is sort of about to die anyway, right? These kind of choices only a human mind can make, because we have the social thing, we have empathy. AI doesn't have empathy yet, right? They will be trained. So these are really, really important issues that we are, I think, struggling with. The other thing with AI is, I mean, I kind of mentioned the Gen AI case of let's look at prior designs and do things, right? Oftentimes, as you know, with large language models, you have this hallucination, you can give wrong results, right? So with a Gen AI based approach, it can generate the wrong design of a phone, right, which will be a wrong design, right? And you will think it's a correct design. AI created it, right? So you have to trust but verify, right? So yes, you should trust this process, but always verify. And so this is where simulation comes in. You trust your AI to generate the right design, but you verify the generated design through simulation.
Right.
That is responsible AI.
Responsible AI. Right, right. So every AI system or the examples which you gave, they would work good only when you ensure that there is certain amount of data quality as an input that you are going to give to the neural networks or the solvers or any system that we are building. But there is always a challenge faced by the enterprises when it comes to data quality. So, what are the critical challenges in ensuring data quality and reliability for AI driven engineering applications, and how can these be addressed?
Absolutely. And this is a very, very important thing that we oftentimes don't have the right data, right? So if you had the right data, you would make the right decision. For example, let me give that example of the space shuttle Challenger that exploded, right?
Right.
I mean, that exploded because of this peculiar combination of things. Here was a tile, and the tile is going, there's a slight crack in the tile, and the shuttle is coming through Earth, right? When it's entering Earth, right? There's tremendous speed, lots of heat, and that tile broke, and that's how the thing extended, right? So, I mean, that situation where that happened with like 1 in 100 million cases, would that particular accident happen? So in the world of simulation and what we call verification and validation, you try to anticipate all the cases and then try to show for every one of the cases it was not going to be possible. But just like in the game of chess, there is just 2 to the power so many cases that it is impossible to enumerate them all. So what happens in the real world, in the engineering world, is engineers take a subset of inputs, right? So they will have 100 runs. Like, so you're designing the Waymo car, right? The Waymo car is driving around San Francisco, taking pictures, and they've driven so far 25,000 miles. The Toyota CEO says that in order for autonomous driving to really work, you have to drive it for 10 billion miles. They will take Waymo 1,000 years to drive a car 10 billion miles, right? It's a long time. This is where simulation comes in. With simulation, you can create effectively all possible scenarios. Right? So suppose you have a Waymo car driving on San Francisco's Golden Gate Bridge at 9 a.m. in the morning when it is sunny, and there's only 2 pedestrians and 5 cars on the street. And my autonomous car drives and it brakes at the right time. Now you want to say, what if it is 9 p.m. in the evening and it is snowing in San Francisco, and there are 15,000 people doing a marathon, San Francisco marathon, and there are 15 dogs on the road, right? And there's a hurricane. I mean, I'm just creating this ridiculous thing. You would have to wait 10 billion years to get to that scenario. With simulation, I could artificially create the scenario. And it's important to artificially create different scenarios, right? So you can have, with data, you can have a lot of data with only the same use case, only sunny days, right? But the real problem will come up with a rainy day. So you have to, with simulation, create enough rainy days and enough sunny days and enough cloudy days and enough snowy days and enough typhoon days, right? And this is a very important fact of normalizing data, because for AI is as good as the data you are fed with. If you are only feeding based on realistic data have biases based on what you have sampled. This is how you can do what is called realistic data with synthetic data created by simulation, which is how, so with AI and simulation, we have sort of 2 paths. One is AI to speed up simulation, and simulation to provide synthetic data to improve AI. And that gets to your question.
Great. I think the last point you said, it's the both way around, that you use the simulation as well as the synthetic part of the generation, which goes as an input, and both the things, they go hand in hand. And the example that you gave, that we can bring that 10 billion miles problem and solve it in a finite time, because we cannot wait for the 10 billion years to have the car driving, using the simulation and the combination of AI.
And with simulation, like you have a million cores on AWS, right? You can spawn off 100 million different simulations, right? One for Golden Gate Bridge at 9 a.m., one for 9 p.m., one for snowy, one for whatever, right? And they're all independent jobs, and you can do this on the cloud today, and that's the power of simulation.
Yes, and there is a lot of data quality to it as well, and the reliability, as we are trying to cover the scenarios as well, to see what outputs we get.
Exactly.
Yes. I think you have already mentioned about the products that ANSYS built, where you used and how you used Gen AI and AI. But just wanted to ask any specific examples of how ANSYS implements AI to improve simulation outcomes and accelerate product development.
Absolutely. So what we have done is we are doing work on the AI topic in the CTO office for the last 6 years. And now this year, we took all those results and we have now announced a set of products in this space. So we just announced ANSYS AI, and ANSYS AI has 3 components. First is SimAI. This is this product that I can talk about, which is You take any generic solver, it could be Fluent for fluid dynamics or mechanical for structures or HFS of electromagnetic. You take any solver, give it a CAD, give it some boundary conditions, and you train the solver, train the AI with same AI on the cloud on AWS, and it just runs 100 times faster. It is physics independent, and it is doesn't have to be parameterized geometry. You can give it any set of CAD inputs and it works. So that's the first tool. Second one is ANSYS GPT, using generative AI, the GPT technology, to provide an interface, easy interface. When a user asks a question, hey, how do I solve HFSS for this problem? There's a response that our application engineer has given. So we take the last 20 years of questions and answers from customers and we put it into Chat GPT and it automatically generates a response for a new question. That's ANSYS GPT. And we are using that technology to not only answer the question in English, but to automatically set the settings of our solver. So that's ANSYS GPT. The third thing is ANSYS AI Plus, which is AI integrated, embedded within our product. So for example, we just launched a thing called Twin AI, which is the ANSYS digital twin product powered by AI with what is called Fusion AI and so on, hybrid analytics, which is a brand new product called Twin AI. So we have these three areas: Sim AI running on the cloud for parametric and non-parametric design, ANSYS GPT and AI Plus, and we have at least 10 different products with AI features in them.
Right, right. I mean, that looks really exciting from how it is sounding, and I'm sure that the users, once they start using it, I'm sure they would see the
So our
enhancements.
customers are absolutely loving across these five verticals. Customers across all five verticals, including healthcare, they are actually using these AI techniques.
Right, right, right. So the last question that I had is more for the aspiring people or the aspirants who really want to come into this field and become data scientists, and they are looking to ask you that what are the key skills and competencies that engineers and data scientists will need to develop to thrive in the AI era.
So one generic statement I'll give is you can never learn all the techniques, right? I mean, at Konverge AI, you have this sort of AI stack or the product development stack. And so there are techniques like data stacks and MongoDB, whatever, they'll keep coming, right? And if you focus on getting MongoDB skills or Python skills, that's the wrong approach. There is no such thing as a universal set of things which may be appropriate in 2024, but in 2029, it will be irrelevant. So the most important thing that I want your readers, listeners to know is learn how to learn.
That's a very important
right
point.
When I went to IIT Kharagpur for my undergraduate, right, I learned programming in Fortran, which is a dead language, right? You guys haven't heard of Fortran. Yes. But I learned how to program. So then when I learned Pascal, it was easy. Then I learned C, it was easy. C++, Python, Lisp, right? So I learned how to learn in programming. And I did not only learn about Fortran, right? That's the important thing. If you are doing product development, don't only learn ANSYS Fluent. Learn how to use Fluid's tools, right? So you could do it. So you could transition one technology to the other, right? Don't focus only on OpenAI ChatGPT. Learn to learn about Bard and Gemini. So the point being, try to learn how to learn.
Yes, I think the approach is the most important part. Like, how do you learn and bring the approach and mindset in? So, having said that, I had, after the discussion, really wanted to ask one more last question to you. So, you spent a lot of time in academia, like you said, and then you decided to shift your career on the industry side, and you worked in academia for a significant amount of time. You worked with the large companies for a significant amount of time, and also spent some time in startups. So which is the best period you see that you personally really enjoyed out of the three, and your views on that?
It is like when a parent is asked a question, you have three children, who do you love the most? You actually love all three.
Yes.
So there were different phases in my life, right? When I was doing academic stuff, I totally enjoyed the teaching and the research. I had more than 35 PhD students, I had 350 papers. I absolutely enjoyed, and based on it, became fellow of IEEE, etc. So I was the academic guy, right? But what I was missing there is I was writing all those papers and supervising all those students, but not really having an impact in a product, right? So nothing was being built. Nobody was using any of the research that was going on, right? So for example, we had this match compiler that we worked on at Northwestern University. We did the publications, it were fantastic papers and so on, but nobody was going to use it. That's when I decided to leave the university, do the startup called Excel Chip, and took that match compiler technology and built a product. And I'll tell you, Ketan, the kick out got, and for that I raised money, $2 million from VCs, hired a team. We had about 20 engineers, and the first product that Excel Chip built called Excel FPGA, and somebody wrote a check for $100,000, right, was much more of a kick than those 350 papers I had in journals, right? Mm-hmm. So it was, wow, it's fantastic. And I did a second startup and so on. Mm-hmm. Now then I worked at HP Labs, and it was phenomenal. It was one of the most prestigious organizations to work for, Central Research Lab of a $100 billion company, right? And the experience of working with about 600 the absolute topmost PhDs working on these interesting big bet projects on sustainable data centers and optical interconnects and memristors and so. It's totally cool. Then I went to ABB, and that was I learned about how Swiss companies work on power and automation and transformers and switchgears. I worked for a French company, Schneider, now at ANSYS. They're all good. I cannot say one of them is better than the other. But when I work for large companies, I miss the academic part, because in academia, you're free to do new things. When I was in academia, I was not having an impact. I feel fortunate as an individual. Not many people get to work in all three. I had the chance to work in all three. So I feel super happy about that experience.
Awesome to hear your perspective on that. Somewhere, the aspiring professor in me has again started thinking about that, whether to shift from this to the other part of the academia, which has always fascinated me.
I'll tell you one thing about academia. This is something in the book, but let me add that at the final comment.
Yes.
Most truly disruptive things that we see in society actually originated in academia. We use the internet, right? But the internet was developed by a people in academia I just mentioning one name, like Professor Len Kleinrock at UCLA, right? He did the first demonstration of the internet, right? He did not start a company. He didn't make any money, but it is his work that created this thing, right? So there are lots and lots of examples like this in the world, right? There's a professor at Berkeley, chemistry professor, who actually created the whole thing about this gene splicing and chemistry and so on, right? She did not make any money out of it, right? Moderna, the vaccine, right, based on mRNA, right, is a thing. But that was based on the research done at Berkeley, for which she got the Nobel Prize in chemistry, right? You go to databases, right? The original work on databases, right, done at Stanford University by professors and so on. So if you really want to do fundamental disruption, we were just talking about Jeffrey Hinton, your conference room, Jeffrey Hinton, Dellert Kuhn, and so on. These are academics who invented the whole technology of AI, ML, and so on, right? And then companies like Microsoft and Google are monetizing it, right? But unless Jeffrey Hinton at the University of Toronto invented the technology of AI and LLMs, we would be nowhere here, right? So I think I just want to salute all the academics here who are creating the wonderful technology for us in large companies to benefit from the technologies.
Very rightly, what you rightly said about that. So that's it. I mean, we have come to the end, but I really enjoyed this conversation and never wanted to stop. But somewhere we have to take the pause. So we thank you, Preet, for spending this an hour's time with us and patiently going through all the questions that we had. And thanks for some amazing business use cases, examples that you gave, and your views on how large companies should use the startups for the innovation, or be it was about your book speaking about it, or it was about the examples you gave of how AI is impacting different industries, the simulation. So we are really thankful to you for recording this podcast with us, and we wish you best of luck for the upcoming journey that you have with the products that you said you're going to launch. Thank you.
Thank you very much. Thank you,
Thanks a
Ketan,
lot.
for inviting me.
Yeah, thank you.
Best of luck. Bye bye.